solutes in each of those compartments. Right? Every compartment is a solution. Cytosol is a solution. Interstitial fluid is a solution. What's the other one?
Plasma.
Blood plasma is a solution, right? There's water and solutes in each one of them. Now what's interesting is that we talk about homeostasis, and this is a very important thing to understand. And I make this mistake sometimes just by common usage of words, and I shouldn't, but homeostasis doesn't mean equilibrium. Equilibrium would be this, right? Here's a cell membrane, and we're talking about the amount of sodium chloride, right? That's a chemical, right? Equilibrium would be what? 7% sodium chloride inside of the cell, and what? 7% sodium chloride outside of the cell. That's chemical equilibrium, right? Is that true? Is that homeostasis? No, in fact, this is homeostasis. That's homeostasis for most cells, is that we have 0.9% sodium chloride in extracellular fluid and 0% sodium chloride inside of cells. This is an incredible disequilibrium, right? So for most solutes, we will have a chemical disequilibrium. And we will have proteins in cell membranes whose job it is to make sure we keep this disequilibrium. So for example, there are sodium pumps just pumping sodium and chloride out all day long because we don't want any inside. For reasons that will become incredibly clear throughout the semester, we don't want any sodium inside of cells, and that'll become clear why. We use sodium to do a lot of stuff, but we need it out here. We also have a chemical disequilibrium, for example, with something like potassium. We like a lot of potassium inside of cells. We don't like very much potassium outside of cells. Similarly, calcium. We like a lot of calcium outside of cells. We don't like any calcium inside of cells. Okay, so homeostasis for most solutes is a disequilibrium. Okay? And that's going to allow the body to maintain its proper functioning. On the other hand, with regard to the solvent and the movement of the solvent by osmosis, we cannot prevent, I can prevent an equilibrium here because once I pump sodium and chloride out here, remember they're what? They're ions. Will they come in? They cannot pass, well, only if I let them, right, a channel or something. Can they pass through a phospholipid bilayer? No, because they're charged. So if I pump them out there, they'll stay out there. But what if I could, I can't, but what if I pumped water out here? If I had a little water pump right here, which we don't, but if we did, and I pumped some intracellular fluid out here, what's it going to do? It's going to come right back in, right? Because it's what? Freely permeable across the cell membrane. I can't keep it out. So because of that, water will always be in homeostasis, in an osmotic equilibrium. It will move to the area where there is always more solutes so that we can maintain an equilibrium with regard to overall concentration of solutes. And so water always moves. It's just going to move. Okay? So cells will always be, in these different compartments, will always be in an osmotic equilibrium. Now, that's important to keep in mind because sometimes would I like to move water? Yeah. Sometimes the body would like to move water. But I can't do it by moving water, but I can do it by doing this. If I wanted to have some water come from outside the cell inside the cell, the only way I can make that happen is if I pump some ions in the cell, and then water will do what? Water will follow it in. Right? Because I'm changing now the concentration here. I'm creating an osmotic disequilibrium by moving these ions in. Water will follow it. It's called solvent drag. I think we mentioned that briefly before, whatever. But the way that my body has to move water is by tricking it. I move ions, water will follow. So water follows ions. keep that in mind here. This osmotic equilibrium, that's the solvent, that's water, right? We're going to just say water follows ions. Keep that in mind. Not just ions, solutes in general, but ions are what we use. But it would also follow protein. If I pump protein out, it would follow sugar if I pump sugar out. For reasons that hopefully become a little more clear. So you get that reason for osmotic equilibrium, osmotic, and then